In this video, we're going to look at specific heat capacity for GCSE science. So the definition of specific heat capacity is a simple one, but it's one that students do struggle to remember. You really need to emphasize this definition as much as possible. It's the energy required to raise the temperature of 1 kilogram of a material by 1 degree Celsius. So in formula terms, E equals mc delta T, energy, mass, heat capacity, and temperature. So it has the symbol C. However, just to confuse things, often we see it as Q is mc delta theta. Right? Q is used for energy in physics a lot in thermodynamics, almost exclusively in thermodynamics, which this is obviously a part of. And then temperature is often theta. And the reason I tell students that it's theta, and this usually does help them remember, is this means degrees in maths, and we're talking about degrees Celsius. And then if we rearrange this for heat capacity, C equals E over m delta T, or C equals Q over m delta theta. So this leads us to our definition of heat capacity. It's the energy per kilogram per degree. In units, and I would encourage you to emphasize this with students, it's joules per kilogram per degree Celsius, or joules per kilogram per degree Kelvin, if you've talked about Kelvin and the Kelvin scale of temperature. This is the unit of heat capacity, and that they can cheat on exams. If they have this unit, they can get the definition joules per kilogram per degree Celsius, right? And anytime you tell students they can cheat, even though they're really just using their brain, they love it and they seem to remember it a bit better. So when I introduce this, what I tend to do is I tend to talk about taking some food out of an oven, and I tend to talk about unwrapping it from the silver foil, and I tend to talk about why the food inside, like if it's a nice baked potato, is really hot and that would burn my tongue, but actually the foil doesn't appear to be hot. And this is a nice discussion because it draws out a lot of misconceptions, which is really important when you're introducing new topics, and it really gets into a nice discussion of what we mean by heat capacity. And obviously the answer to this is the foil has a tiny mass, so it really can't store much energy. Therefore, when you touch the foil, there's very little energy transfer to your skin and you don't feel much or anything. Whereas the food has a large mass, it has water in it, which has a large heat capacity. It stores a huge amount of energy, and it's that energy transfer that will burn us. So it leads us also to this difference between heat versus temperature, which is a really important distinction. Heat is energy, or an amount of energy, and temperature is a measure of hotness, or a measure of how much energy. That's maybe a better one. Measure of how much energy something has. Depending on how able your class is, you could talk about temperature as relating to the vibration. We should be talking about all our classes really, the vibration of particles, and the higher the temperature, the higher the kinetic energy. And ultimately these things are related. If you do A-level physics, you look at this formula, which is basically showing that energy is directly proportional to temperature with this constant. And I would not mention this outside of maybe triple classes, but there is a direct relationship here. So energy is a measure of, energy is a measure of how hot things are. So there's one other important distinction for this. What is heat capacity not? Heat capacity is not the same as thermal conductivity. So these are different things, and students do get these mixed up. Heat capacity is a measure of energy storage. How much energy can something store? Does it store a lot of energy? Does it store a little amount of energy? Whereas thermal conductivity is the rate of energy transfer. And this appears in the Year 9 energy topic as well, rate of energy transfer. So you can talk about, having a large container and a small container full of maybe, water or something, and a container where the water is coming out of a small hole where obviously it's going to be transferring slowly, or a large hole where the water is going to be coming out really, really quickly. And you can get this idea of a transfer, the rate of transfer versus just storing it here. We then move on to calculations. So more able students will be able to use this formula with very little difficulty, whereas lower sets might struggle a bit. So I'd encourage you to maybe use this kind of approach where we think about 1 kilogram, and then we say for every degree Celsius, you want to increase its temperature, you need the heat capacity, that amount of energy. So let's look at an example. Let's think about water here, because water is very commonly used. This has a heat capacity of 4,200 joules per kilogram per degree Celsius. So 1 kilogram by 1 degree Celsius, you would need 4,200 joules. If you wanted a rise of 2 degrees Celsius, you would need 2 times 4,200, which would be 8,400. If you wanted a rise of 3 degrees Celsius, you would need a rise of 3 lots of this, etc., etc. Okay, and then you can scale this up to an arbitrary change in temperature. All right. Similarly, if we have 2 kilograms of something, then what do we need? We need 4,200 plus 4,200 for every degree. If we had 3 kilograms, we would need 4,200 plus 4,200, etc. And again, once you've done this 3 or 4 times, then it's easy then to generalize, and you go, right, 18.7 kilograms, and then they get it. But if you just jump ahead too quickly, they do really struggle with this idea. And especially when it comes to a large change in temperature and a large change in mass, they'll struggle to get both these things in their head at the same time. So it's worth breaking it down. Right, first we're going to think about every single degree for 1 kilogram, then how many kilograms are there in total. Now, another area for confusion is when students see this in chemistry versus physics, because in chemistry we always use SI base units or SI units where we're using kilogram, whereas in chemistry we're not always using the base units because, quite rightly, we're often measuring small amounts of things. So when we're talking about the heat capacity in water, for example, and we'll keep with water just because it's one of the most common things that comes up, in chemistry, it's given as 4.2 joules per gram per degree Celsius, whereas in physics, it's given as 4,200 joules per kilogram per degree Celsius. It's worth highlighting this difference here, and that's an entirely reasonable difference because of the point of what chemists are doing or what they're working with every single day. And then one other thing that's a bit of a tangent, it's not on the GCSE syllabus, but it's useful to know in everyday life, and students will obviously come across the word calorie. 1 calorie is equal to 4,200 joules. The definition of 1 calorie is the energy required, you can probably see where this is going, to heat 1 kilogram of water by 1 degree Celsius. And then it's usually worth saying that actually, if you look on the back of a food packet, when we see calories, we actually usually mean kilocalories. So if it says, 15 calories, it probably actually means 15,000 calories, and it doesn't therefore mean this many joules. It mean 1,000 times this. So the other reason for introducing calorie is because then when we actually come to measure heat capacity experimentally, we use calorimetry or calorimeters. And it's useful for students to make the link between this this part of the word and calorie. So how do we do it experimentally? What we're going to do is we're going to get ourselves a block of metal. We are going to stick a heater, an electrical heater in it. And we are also going to stick a thermometer in it. And then on this heater, we're going to connect it in the circuit where we can measure the potential difference across it. We can measure the current through it, and then we can connect it to a power supply. Okay, not the clearest diagram. A lot of the diagrams you see in textbooks, again, are not super clear. So if you're doing it this method, you need to really think about setting up a good, clear demonstration circuit with everything spread out, different color wires for everything. So you could use green wires for this. You could use red wires for everything else, for example. There is an alternative to this. You can actually just get your metal block, get your thermometer and heater, and then you can connect your heater straight to a joule meter, which will measure the energy input directly. So this is obviously a lot easier for students to see. That they should be aware of both of these, because this could well be asked. So how do we work out the heat capacity? Well, there's an easy way and a slightly more difficult way. The easy way is to use the joule meter, and we simply work out the energy that goes in using the joule meter. We measure the change in temperature using a thermometer, and we use the mass balance. It's always mass balance, it's never scales, to use to work out the mass, and then we can work out heat capacity. Slightly more complicated method, if we're doing this here, what is the energy input? We need to use the electrical energy formula, which is IVT, or ITV is a bit more memorable. Again, same idea, temperature change with a thermometer. You measure a period of time using a stopwatch, measure the voltage and current over a period of time, measure the mass, work out heat capacity. All right, that's okay. That will give us a measurement. There's nothing wrong with that, and students should know this. But a slight improvement is actually over time. If we measure the energy input over time, so if we measure the temperature over time, sorry, I've completely messed this up. What we actually want to do is we want to measure the energy input, and we want to see how the temperature responds. This is the graph, energy against temperature. And then what you'll see is over a period of time, we will get this happening. So energy is obviously always increasing. The temperature will start by not doing much. It will start slowly, and then eventually, after a period of time, there will be this constant increase in temperature. So this obviously represents the fact that the heat takes a bit of time to travel out from the heater, takes a bit of time to get to the thermometer and heat it up. So now what we can do is we can take the gradient of this constant section, and we say that the gradient is equal to E. Sorry, no, we don't. We say the gradient is equal to mass times the heat capacity. Okay, so what we're really saying, you don't need to do this with students. You can if you want, especially if it's high ability. We're saying y equals mx for this constant section, right? We're going to ignore this intercept. Y equals mx. The y value is the temperature, m is the gradient, and x is the energy. So if I got this the wrong way around, the gradient. Yeah, sorry, I've got this the wrong way around. The gradient is 1 over mc. So the gradient is 1 over mc because from this here, we can see that E equals cm delta T. So 1 over m delta T. Sorry, I'm completely messing this up. Over mc. Energy is C m delta T, or energy over m delta T is C. So 1 over the gradient is mc. So you can find the heat capacity from that. This is obviously a better method because there are multiple readings, and we've got this graph that's kind of giving us this average of our multiple readings. And then finally, you'll want to talk about errors here. So errors could include not having insulation, which it can easily be improved by putting insulation around it. You could improve it further by making sure there is no air gap here by just putting in a bit of oil. So that means that no energy is wasted in air. Same as around the heater, you can just put some oil in to stop it heating up the air. You need to obviously make sure there is little or no heater above the metal block. And you need to ensure that these values are not fluctuating too much, which they will a little bit, but you can either take an average or you can accept that it's just an inevitable part. When you do this, you get a reasonable value. You should find that metals have a value of hundreds of joules per kilogram per degree Celsius, which is significantly less than water, which is 4,200. So this is a nice discussion, and it links into wider science. The metals obviously heat up and cool down really easily. Okay, it's not to do with them being thermally conductive as such, but it's their heat capacity. Water takes a huge amount of energy to heat up and cool down. So water makes a good coolant, for example. You can also talk about the fact that water doesn't freeze very easily because of this fact. And then you can talk, even going to talk about oceans, the Ice Age, icebergs, and loads of other things if you want to.